Hello, and welcome to the video lecture for topic 10, alkene isomers and chirality. So far this semester we have seen a few different types of isomers. We started off by considering constitutional isomers, where we have the same types and same number of atoms within a molecule. However, the atom connectivities or the bond paths within two different molecules will be different. And so that was the first type of isomer that we encountered. We just recently covered the topic of conformational isomers, where we can do two different 3D distributions of atoms around a molecule by making a single bond rotation. And so our conformational isomers we just refer to as conformers. In topic 9, you were introduced to the idea of cis and trans isomers when you have two substituents on a cycloalkane. And so now these two types of isomers, right, are going to be what we call stereoisomers. There is some sort of stereochemical difference between two molecules where the bond paths may be the same. And so these now introduce stereoisomers. And we've seen so far cis-trans isomers for cycloalkanes. However, this concept of stereoisomers extends far past just this one example we've seen so far. And stereoisomerism is a very big and important point in organic chemistry, because the specific, as we say, stereochemical geometry or stereochemical arrangement within a molecule can lead to very, very different properties and very different behaviors. The most prominent and most famous of these stereochemical issues is in the pharmaceutical thalidomide, which years ago was used as an antiemetic for women who were pregnant, but turned out one enantiomer, and we'll learn this word towards the end of this video lecture, one enantiomer of thalidomide caused horrible, horrible birth defects. One enantiomer of thalidomide was perfectly safe. And so this concept of enantiomers is very important in organic chemistry because the properties of molecules can vary wildly based on their stereochemistry. But to begin topic 10, we're going to start off with looking at alkenes. And so alkenes can have two different types of geometry, and these geometries, right, this arrangement of groups around an alkene, we use two different nomenclatures to describe them. One nomenclature, which we'll look at first, is called cis-trans nomenclature. And the other nomenclature that we'll see in a little bit is known as E and Z nomenclature. So to begin, let's just focus on cis and trans for an alkene. So let's just put up a model alkene. So I'll have a carbon atom that's double bonded to another, and off of that carbon atom I'm going to put four different groups. So we'll have A, B, X, and Y. Now, A and B and X and Y can be the same or different. And if all four of these groups are the same, there's really no stereochemical implications and there's no stereochemistry to this alkene, right? We would just say that this is an alkene, right? All four of these are the same. It's just a carbon-carbon double bond somewhere in a molecule. However, if there are two of the same group on opposite sides, so for example, if A is the same as X, but it is not the same as B, and it is not the same as Y, we have two groups that are identical on one side of our alkene. So here now A and X are the same on one side, top versus bottom of the alkene. In this case, these two groups are on the same side, and similar to what we saw with cis-trans isomers and cycloalkanes, we would say that this is a cis alkene. Right? We would describe its stereochemistry as being cis. However, if we take now that same alkene and do a slightly different scenario, so here I have my two carbons, and I'm going to put in my four substituents again, A, B, X, and Y. But now this time, I'm going to have A be the same as Y. So A is the same as Y. It is different than B, and it is different than X. Now I have two substituents that are the same, but are on opposite faces of this alkene. One is up on top, and one is down on the bottom. Similar to how we had one group on top, one group on bottom on a cycloalkane, here again we would denote this configuration as trans. Now this only works if A is the same as Y, we get trans. If A is the same as X, we get cis. If A equals B, or if X equals Y, we don't have anything to describe it because we have two of the same substituent on one carbon atom. And so for these cases, A is the same as B, or X is the same as Y, we have no descriptor. Now again, it really doesn't matter what B and X are, so long as A and Y are the same. And here in this example, it doesn't really matter what B and Y are, as long as A and X are the same. We can use these terms, cis and trans, to describe these two scenarios, right, when two substituents are the same, one on each of the alkene carbons. Well, what happens if we have four different substituents on this alkene, right? We can't any longer use our cis and trans nomenclature. We have to now move to a different nomenclature, and that's going to be our E and Z nomenclature. So let's just take a moment and see how that looks. So for our E and Z nomenclature, I want to start off with just going into what these terms E and Z mean. So both of these descriptors come from German words, E for entgegen, and just make sure I've got my spelling right here. Which comes from the word apart, and Z comes from zusammen, and for those of you who speak German, I'm sorry if my pronunciation is off there. Zusammen, which means together. And we're going to see that E is very closely related to trans, and Z is very closely related to cis. However, since the groups that are attached to the alkene are all different, we can no longer use that cis and trans label. We have to use the E and Z labels instead. So let's again just put up our generic alkene, right? So here we have our carbon-carbon double bond. We're going to put our same four fictional groups off of this alkene. A, and B on one carbon, and then X and Y on the other. Now, since all four groups are different and we can't use E and Z, we have to find some way to differentiate between the two substituents on one carbon and the two substituents on the other. And we're going to assign priorities to each of these groups based on what they are or what atoms they contain. Now, the system for assigning priority is called the Kohn-Ingold-Prelog convention. It's abbreviated CIP rules. And in just a moment, I'm going to get into how the CIP rules are applied. But to just finish up how to label E and Z, we look at each carbon of the alkene individually. So I'm going to start off with the carbon that has substituents A and B. And we'll see how to apply our CIP rules, but eventually what we're going to find is that one of these substituents, for example A, will be of higher priority, and we'll give it a rank of priority 1, and the other substituent will be lower priority, we'll give it a rank of 2. Here on our other carbon of our alkene, we'll repeat that process. Right now I'm just arbitrarily assigning these priorities as 1 to X and 2 to Y. And what we'll see then is if we imagine a plane dividing the alkene top and bottom, in this example we have the highest priority groups on the same side of the alkene. So here, right, A has higher priority, X has higher priority, they are on the same side. This example would be a Z alkene. And if I were to recreate this scenario, but switching priorities on one of those carbons, so there's my alkene, there's my X and my Y, and here now my A and B. However, this time for our other fictional alkene, we have group A with priority 1, group B with priority 2 on this carbon, and then we'll have group Y with priority 1 and group X with priority 2 on the other carbon. Here now, if we repeat the process and draw our imaginary plane dividing our alkene top and bottom, we see that our highest priority groups are on opposite faces of that alkene, right? And so they are apart from each other, which would make this an E alkene. So E similar to our trans, Z similar to our cis. However, since we have 4 different groups, right, on this alkene, that none of them are the same, we can't use cis and trans anymore. We have to use E and Z. So I'm going to take a pause here, and when we get back, we're going to go ahead and see how we determine priority for groups on an alkene. So for assigning priority to these groups on the groups on an alkene, we're going to want to use what are called the Kohn-Ingold-Prelog rules, or simply CIP rules. Okay? And now, the CIP system of priority is very different than IUPAC naming priority of functional groups. CIP rules don't rely on functional groups. They look at each individual atom and every single bond to be able to distinguish priority. So don't get your CIP rules confused with your naming rules, right? Our CIP rules are very different. We're going to be using them in this topic and the next topic, and throughout the semester whenever we need to assign stereochemistry. So, CIP rules. Number 1, first thing we look for to determine which group on one of the carbons of an alkene is of higher priority is look at the atom directly bonded to that alkene carbon. And the higher priority atom is the one with the larger atomic number, right? So higher atomic number, higher priority. All right. Rule number 2. If if both of the atoms directly bonded to that alkene carbon are the same, we move on to what we call the next shell, right? So second shell, and again, we look to see which has highest atomic number, and that's going to take priority. So in our second shell, highest atomic number is higher priority. Rule number 3. Treat double bonds and triple bonds as 2 or 3 single bonds. So if I have a carbon double bonded to an oxygen, right? Carbon is that first atom off of the alkene, right? And then my double bonded oxygen is the second atom off of that alkene. I would say that that carbon is actually single bonded to 2 oxygens. And don't worry, we're going to go through examples where we apply these rules. All right. And speaking of going through examples, we've come time for it. So we're going to take a look here at a pretty complex alkene with some relatively complex substituents. Again, this is a fictional molecule that I just made up. I don't really know if it exists or if it could be synthesized, but it does a great job of demonstrating how to apply our CIP rules for priority. So here, just to give a simple line structure, we're going to have carbon double bonded to carbon. Off of this one, I'm going to put a nitrile group, and then I'm going to have another carbon with an amine, and a nitro, and we'll put another nitrogen here with a hydrogen off of it, double bonded to a carbon with 2 methyl groups. Right? Again, I am purposefully in making this very complex so that we can see how to apply all of these rules. On my other carbon, we'll have an aldehyde, and we'll have a carboxylic acid. So let's just attack each side of the alkene one at a time. So the first thing I need to do is I need to look directly off of the alkene carbon and see what that first atom bonded to it is. And so that's going to be our first shell, right, application of rule number 1. So if I look at my first shell, and I'm going to expand over here how this carbon atom is. So in green here, I have my alkene carbon. I'm not going to worry about what's on the other side of the alkene for now. And I'm just going to draw the 2 atoms directly bonded off of this carbon. So here now I have a carbon atom from this aldehyde and a carbon atom from this carboxylic acid. Now these 2 obviously have the same atomic number, and so we can't assign a priority to them. That means we need to move to rule number 2 and look at our second shell. So for our second shell, off of my aldehyde carbon, I have a double bond to an oxygen. And so I'm going to treat that double bonded oxygen as 2 single bonds. So I have 1 single bonded oxygen, there's my second single bonded oxygen, and then finally off of that same carbon, I have a hydrogen atom. Now, for my carboxylic acid carbon in my second shell, I have a direct bond to an oxygen, and then I've got a double bond to an oxygen that I treat as 2 single bonds. So there's 1 and there's 2. Now I can begin to look and see where my highest atomic number is to assign these 2 priority. So we saw in our first shell that our carbon atoms were the same. We ignore those. And then we start with each substituent comparing highest atomic number in our second shell. So my highest atomic number on this carbon is an oxygen. I have an oxygen as my highest atomic number on my lower carbon. These two would cancel each other out. Moving on to my next highest, again I have oxygen on my upper carbon and oxygen on my lower carbon. These two would cancel each other out. And then finally, here I now have a hydrogen on my upper carbon, an oxygen on my lower carbon. This oxygen wins, and so I can assign my carboxylic acid priority 1 and my aldehyde priority 2. Let's move on now and take a look at this right-hand alkene carbon. So now I'm going to put in my alkene carbon on the right-hand side, and I'm going to draw in the two atoms that are directly bonded to it. So directly bonded to this carbon, I have another carbon atom, and one down below. That's this carbon here and this carbon here. Those are of the same atomic number, so I need to move on to my next shell. Well, for my upper carbon, I'm triple bonded to a nitrogen, and so that means I need to look at my second shell. I need to treat that, as 3 single bonds to that nitrogen. Here in my lower carbon, again, I have a nitrogen, and a nitrogen all directly bonded to that carbon. So there's one nitrogen, there's my second nitrogen, there's my third nitrogen, and I can tell already that now I have to move on to my third shell. So this is repeating step 2, right? My first shell, I couldn't make a distinction between these two carbons. My second shell, I couldn't make a distinction between the different nitrogens. That means I need to move on to my third shell. So for the third shell, we have to treat this carbon triple bond nitrogen in a special way. If I look at this nitrogen, it's got 3 bonds to carbon. So I pick one of my 3 nitrogens here that all represent really the same atom in my actual molecule. And off of one of them, I put, and I'm going to use yet a new color. One second. Here we go. So I'm going to now use pink to denote my third shell. And I go off of one of those nitrogens, and I put 2 carbon atoms, because my nitrogen is bonded once to carbon, twice to carbon, 3 times to carbon, right? So now pink is going to be my third shell. If I now move to this amine nitrogen, I see that in my third shell, I have 2 hydrogen atoms. I need to know my structure of NO2. So NO2 is going to have a nitrogen single bonded to an oxygen, a nitrogen double bonded to an oxygen, which I'm going to treat as 2 single bonds. Finally, over here, this nitrogen is, I've got 1 bond to a hydrogen atom, and then I've got 2 bonds to a carbon. So I'm going to treat those as individual single bonds. So now we can begin to take a look and see here in our third shell which group is going to take the higher priority. Okay? And so we should just do this by starting to cross off atoms, right, in our third shell that are going to be losing priority by atomic number. So in our third shell, for this nitrogen, we have 2 carbon atoms, right? So carbon's an atomic number of 12. I'm just going to put that there as a reminder. Hydrogen's an atomic number of 1. Oxygen is 16. And now here, this carbon is also 12 and 1. So if we see here, right, obviously this nitrogen can't win the battle because it's just connected to 2 hydrogens, so it's going to have a low priority. We now need to distinguish between this group where we have carbon, this group where we have carbon, and this group where we have oxygen. And so obviously, right, we know that oxygen has the highest atomic number, which means that in our third shell, this set of atoms would win the priority, and that works all the way back to the carbon directly bonded to the alkene, telling us that this group is going to be priority 1, and this group is going to be priority 2. Right? Another way to do this would be to say this carbon and this carbon tie, this nitrogen and this nitrogen tie, this nitrogen and this nitrogen tie, this nitrogen and this nitrogen tie. I have to move to my third shell. Here I have a hydrogen, here I have an oxygen, so these three lose. Here I have a hydrogen, here I have an oxygen. These two lose, and then finally here I have carbons, here I have oxygens. Carbon is lower atomic number. This is the group that has the highest priority based on atomic number, and we work it back to the carbon, attaching it to the alkene. So finally we can go up to our original drawing now, and we can say that this group is priority 1, this group is priority 2. If we draw our imaginary plane dividing the top half and bottom half of the molecule, we see our higher priority groups are on the same side. That makes this a Z alkene. Again, I chose these substituents because it would force us to go to the third shell on one side, second shell on the other. We can usually make these distinctions a little bit quicker, but you should be able to do this analysis all the way out to a third or even a fourth shell if necessary, right? And so this application of Kohn-Ingold-Prelog rules is going to come back in topic 11 when we start looking at the chirality of sp3 carbon atoms. But to introduce that topic and what chirality is, we're going to do that right here in just a moment. All right, and so to wrap up topic 10, what I'd like to do now is kind of fill in our isomer list a little bit more of what we've seen so far today, and then move into the chirality of sp3 carbons. And so in the world of stereoisomers, in topic 9 we saw cis-trans isomers for disubstituted cycloalkanes. Today we also got to see cis-trans isomers for alkenes and cis-trans isomer, E and Z isomers of alkenes. This list is going to continue to grow moving into topic 11, but that's where we'll pause on our isomer list for topic 10. So to wrap up topic 10, I'd like to talk a little bit about sp3 hybridized carbons. And this has been a topic, right, that we've been talking about now for a while, but specifically, right, what is going on if an sp3 hybridized carbon has 4 different groups attached to it? So there's my sp3 carbon, and again I'm going to use these same arbitrary and artificial groups A, B, X, and Y. Now this time though, I'm going to put X coming out of the board towards you, and Y coming behind the board towards me. Now, there are 2 possible arrangements for these 4 groups. One which I've shown you here, where X is coming out of the board towards you, and Y coming behind the board towards me. But I could also swap those 2 groups and have a different arrangement. So here now I have A and B in their same positions, but now out of the board towards you, I'm going to put Y, and coming behind the board towards me, I'm going to put X. So I've just swapped the positions of X and Y, right? If you look at this, you would think that I have, these can't be constitutional isomers. We have the same bond paths in the molecule. They are not conformational isomers. We can't do any single bond rotations to convert one to the other. And they're not really either, there's no cycloalkane and there's no alkenes, so these cis-trans EZ isomers don't really apply either. But what we should notice is if I take this molecule and I rotate it 180 degrees, what ends up happening is that I have created a mirror image of this molecule over here on the left. Of this molecule over here. So let me now take this and just rotate it around. I'm going to hold A steady where it is, and I'm just going to rotate B, X, and Y so that my X and Y are now pointing towards the X and Y of the original. So that would now look like C, there's my carbon atom, A has stayed in its place, and now I'm rotating those bottom three substituents, and what I have now is X coming out of the board towards you, B here in plane with A and C, and Y coming behind the board towards me. This molecule here and this molecule here are mirror images of each other if I consider this to be a mirror plane. Right? I can draw, if I moved it up, I could draw a straight line connecting Y, a straight line connecting X. Those lines are perpendicular to my mirror plane, and the same with A and B. These are now two mirror images. However, if I try to lay one directly on top of the other, I'd see that they are what are called non-superimposable mirror images. So essentially, if I take this depiction here and just slide it over, we'll see that B lines up with B, we'll see that B lines up with B, A lines up with A, moving this direction, but now X lines up with Y, and Y lines up with X. And so we have created a mirror image. I can't superimpose that mirror image over the original. And so we use this term a lot, that these two molecules are non-superimposable mirror images. This phrase, non-superimposable mirror images, right, has a very special meaning to us in organic chemistry when we describe stereoisomers, and it describes the relationship between these two molecules, right? They are not constitutional isomers, they are not conformational isomers, they are not cis-trans or EZ isomers, but they are what we call enantiomers, right? So these, when we have two molecules that are non-superimposable mirror images, these are enantiomers. And this is only true if all four groups on the carbon atom are different, right? So if A is different than B, is different than X, is different than Y. If any of those are the same, if A is the same as B, or if X is the same as Y, right? We can't set, any stereochemistry. We can always create a superimposable mirror image. So we don't worry about that. But when we have this scenario, a carbon atom, sp3 hybridized, 4 different groups attached to it, I can create a non-superimposable mirror image. I can create its enantiomer. That means that this carbon atom is chiral. Right? And chiral carbon atoms are very important to us, right? We're going to see chiral carbon atoms throughout the rest of the semester. You're going to see chiral carbon atoms next semester as well. For those of you who are in the biological sciences, this concept of chirality is what makes it that only one set of amino acids work in our body. Only one set of sugars are digestible for us, right? This concept of chirality has extreme implications in all biological systems, and so a fundamental understanding of chirality is going to be really important whether your path lies in chemistry or your path lies along a biological science, right? Either way, chirality is very, very important. Now I'm going to stop here in our conversation about chirality and sp3 hybridized carbon atoms, right? This is going to play into our stereoisomer picture, but we're going to get a lot deeper into this concept and this topic when we get to topic 11. So as always, thank you for watching. If you have any questions, please feel free to bring them up in conference, lecture, or office hours, and have a great night.